and we are going to look at this external DSL again. So I'm going to quickly put together the xtext grammar for this. So let's do a new xtext project. And this is entity plus. Well, that's actually entity plus, like this. Dot entity plus language. And this is EPL, entity plus language. And I have my example here. So we have our externals first and then the entities. So one problem that some of you had was with ambiguous grammars, because the require is actually something that doesn't attach to an attribute, but it's just another member. If you want to be able to attach a require to a specific attribute, which might make sense depending on how you want to model it, then one way to do it is to have a specific keyword like with and then a require, because then this syntactically tells us that, oh, the one require that comes just after this one belongs to that attribute. And it becomes unambiguous what we mean, and this is what our LLK parser prefers. But let's make it like this. Oh, sorry, we don't want to do that. So, EPL. So we have our externals, and we say we want a whole bunch of externals first, and then entities, a whole bunch of it. We want at least one entity like this. Okay, and let's have external first. So an external has the keyword external. Let's just look at it. Then there's a name, parentheses, and some types. So external, name, and we use a special xtext name thingy to make it something that has a global name in our DSL program. And then left parentheses. And then we want the parameters. So params, and then we use plus equal because there might be many of them. And at first there's just one, and that's a type. So types are what we can write here. And then there might be more. And we can have any number of them. If for every one of them there must be first a comma, and then one more type. So in the end here we have a list of all of the types that were separated by commas that were put here. We create the type rule. So a type is either an, let's do it like this, an int type, integer. So this is going to create special objects for each of these. So there will be an object, a class in my meta model called int type. It doesn't have any attributes, but we're going to get an instance of that whenever we write integer and string, and then we had decimal type decimal. So in my params there's going to be a list of objects of type. Sorry for the double type thing. And each of those are either going to be int type, string type, or decimal type objects that don't have any attributes. We could also have, if I didn't want it objects like this, I could also have like I could have called it for example t equals integer like this. Then there would be if I had that for all of them, like this, then it's just going to be a type object, and that's going to have a single attribute t. That's going to be either integer, string, or decimal. So which do you prefer? The first one or the second one? Any preferences? Let's have a vote. Who votes for the first? Okay, that's about 6, 7. Who votes for the second? Not so many. Okay, we go back to the first one. Good. Now, so that's it for the external. For the entity, well, we have the usual entity stuff, plus we have this require thing. So an entity, that's an entity with a name, that's an ID, and then there might be a base entity, base equals, and this is then going to be the name of an entity like this. Left bracket, a whole bunch of members, and a right bracket. Okay, members are either an attribute, a relation, or a require. So that's where I put my require, and in my language that's the only place I'm going to put a require. Okay, an attribute. An attribute has a name, and here, I mean, you can call it name if you want to. It's okay, but I explicitly don't use it here to make it clear that it doesn't do the magic name lookup for attributes like we talked about last time, because several entities might define the same attribute name. So I'm going to call it a name here. I personally like this. It's sort of a programming idiom that I use. Makes it clear. That's an ID, and then there's a colon, and then there's a type, which is a type. So that's an attribute. A relation that has the keyword relation. Let's look at what they were like otherwise, and then the name, colon, the multiplicity, and the type. So then there's a name and our name equals ID, a colon, multiplicity. So that's a specification of the multiplicity, how many, 2 dots, and then one more. Now some of you added that the multiplicity is either 0, 1, or star. And if you add that, then 0 and 1 become terminals that are distinct from the int terminal. So this means 0 and 1 are no longer integers, which is, it might be okay in your program, but usually that's not what the program expects. They could probably write 0, 0 and 0, 1 to get 0 and 1. So you could get around it. But we could also say that, well, we might actually allow any kind of multiplicity here. I mean, you can do that in UML. You can say a car has 4 wheels, for example. And you put a 4 on the thing. Or it has more than 4 wheels if it's a car. Or maybe more than 3, depending on how we define cars. So, I think we should say it as a from, which is let's just call it multip, because multiplicity is really long. And then there's dot dot, and then there's 2, which is also multiplicity. And then there's a type, which is the name of an entity, like this. And the multiplicity, that's either a number or a star. So that might be a star, like this. And we're using the same program style as before, or it's a number, and then we have value equals int, like this. So here the from and the to are both of the type multip, and multip is has 2 subclasses, star and number. Star doesn't have any attributes. Number has an attribute value, which is then whatever integer we had. That's a question.
Like the name before, will the star subtype thing be a global, or will it just be within multip star exists?
Star is the name of a class in your meta model.
Yeah, so it can only be in there. If we were, for instance, to define...
I can write it somewhere else if I want to, like this.
Yes, and that would be a new one, or would it be the same?
it's the same. So you can get some very funny subtype relations when you build up these grammars.
Yeah.
And there's a well-defined algorithm for how xtext does it that we can look at, but you can also go, I mean, basically it builds it up from interfaces.
Okay.
So you can do any kind of funny relations you want.
Yes.
You can control it. Like here I could say require returns multip. Like this. This means that, oh, this actually, even though I call the rule require, it's actually a multip thing that it returns.
Okay.
That doesn't make sense here, but it can be very useful for the expressions. If I want to say that, if I want precisely the meta model that I have on the blackboard behind me, which is that an expression has been up and int and var as subtypes, I can force xtext to give me precisely that meta model by controlling what types I return from the rules. So this is for tuning your meta model. It doesn't have an influence on how it passes the program, but it has an influence on how it generates your meta model for you. But we don't want that here because it doesn't make sense, but let's see, we might make use of it later on. So, and this is of course another thing you could find if you looked into the xtext documentation. So require has the require keyword, and then we get to the exciting part, of course. Now we get the huge mess here. But now we know better how to handle this. So, an expression like this is actually simple. We have something, we have relational expressions, and then we have and or between them. So this is actually a simple, almost a degenerate version of the example we saw here. So a require has a compare expression and oh, I have to be a little bit careful. Let's just actually it has a what's it called? I forget the word. A requirement. Okay, and a requirement. Sorry. So a requirement. Now we have to do the same thing as before. So that, well, that must be at least one of these comparison things. So that has a compare equals comparison like this. So let's try and build it up. And then there might be more if there's an and or an or, right? So there might be an and let's call it a logic expression. Okay, so a logic expression dot left equals current. So this is the same as before. So now our logic expression has two comparisons. And our operator equals, that's going to be either and or. It's a little bit compact, but I think it works. It's and or, so we're going to say this as a string. If you wanted to break it up into objects, we would have to use some subrules here. Let's just keep it like this for now. And then the right is equals to, is going to be a requirement. Okay. Now these can be a little bit tricky to get right. I think this is it, but let's see. Now comparison So what you're saying here, we have a long list of things with ands and or between them. Right now we don't allow parentheses for the ands and the ors, and we don't have any precedence between ands and ors. So it's not completely what we want. But let me just, so you get a sort of a picture, and let me say a comparison. Well, this is something like age is greater than 15 or age is less than 76. So this is and comparison has a left, which is a term. It has an operator, which is a comparison comp operator like this, and a right, which is a term. Our comparison operator, that might be less. If we have less, it might be more. More if we have greater than. Let's call it less than, greater than, less than equal if we have less than equal, greater than equal, and of course I trust you to point out if something looks weird here, because greater than equal, or just equal if it's an equal like this. Okay, and terms are either variables or numbers. So a variable has a name, which is or is a vname, is an id, and number has a value, which is an int. Okay, so requirement, that's a long sequence of comparisons. This is the left factored version I have here. We can look at doing parentheses and precedence for our logical operators. Usually we give and a higher precedence than or if we're doing sort of a Boolean algebra. So we could do that here as well. And this is all built up of these comparison terms. And the comparison terms, I think they're just going to be atomic here. There was also, of course, the possibility to call a function like this. I haven't implemented that yet. And I think these were two different cases, so let's call this one a require exp, and then say a require, that's either a require exp or a require external. A require external, that's for example here the name of an external, and then a bunch of identifiers. So this is what do we call it? External. Function. The function's call is this one. It's a left parenthesis, and then we have the same pattern again for the arguments as we've seen before. So args plus equals, and now we're just going to have identifiers, because we don't, from inside our BNF, we don't know what are the locally defined names. We don't have a local notion of a scope, so we don't know which names would be legal here. And then we have the same pattern again as before, that we can have more arguments if there's a comma. And when there's a comma, there must be one argument. Like this.
Should you move the required line up into the required?
Should I, what, sorry?
The required in the required expression. Down. No, go down. The text.
Oh, yes. Thank you. Yes, we can do. This is And this is where, because it's an if we had an LL1 parser, it can only look at one token, then it wouldn't know what to do with these two here, because it starts with the same thing, require in both cases. But because we have an LLK parser, where depending on your grammar, k might be smaller or bigger, here, because we have we can look ahead more than one symbol, we can then find out which of these two it is. Okay, so this is our basic left-factored grammar. We don't have parentheses yet, and we don't have precedence between the and the or. So let's look at that. So let's have, so actually rather than calling this a requirement, let's call it a, let's see, does it do, no it doesn't, sorry. It doesn't do the refactoring of renaming. So this is actually, so we have disjunction, so that's a bunch of ors of conjunctions. They're the things that have ands between them. Do you know these words? Disjunction, conjunction? Well, you know them now. Okay. Let's try it like this. I haven't actually done this with this example before, so it's going to, it might, let's hope it works. Disjunction. So, disjunction, that's a bunch of stops with ors between them. I think this should actually be a disjunction, by the way, here. Okay, so now we have a bunch of stuff with or between them. And the stuff that we have are conjunctions. So a conjunction, that's a bunch of stuff with and between them. This is the same pattern as we have on the blackboard with multiplication and addition. Now we're just doing it with or and. Okay? And so maybe rather than compare, we call it so-called exp. That's a good word. Actually, I'm not sure we need that actually. So now, so in this case, we're saying a disjunction might be just a conjunction if there's nothing more. If there is something more, then it's actually a logic expression with a left and a right. And an operator. I do need to remember what the operator is. Conjunction. Now my basic thing here is a might be a, let's call it a term, or then there might be a logic expression dot left. This is now for the and a right, which is a conjunction. So now I have a bunch of ors. That's my weakest. That's at the top level. I have a bunch of stuff with or between them. The stuff are conjunctions, so things with and between them. And what I'm adding together are terms. And a term, or did I use term somewhere else? Oh, sorry. This is a logic term. Okay, a logic term. Because a logic term, now I need to have the parentheses. A logic term is either a comparison or a parenthesis and then disjunction, like this. Is that bad? Let's see. Okay, so there are limits to what we can do here. So I think the fix here is to say these are all expressions. No? Maybe I don't, actually this is redundant here. Right? So require disjunction. Okay, returns exp. Still complaining. Okay, so that's that's from before. I think it's okay here. Okay, now we're saying, oh, these are all just expressions, because before I was trying to take the rules and make them into a subclass hierarchy, where logic term was a subclass of conjunction, was a subclass of disjunction, and then because logic term could also have disjunction, then we had a cycle in our subclasses, which is bad. The returns tells it, oh, that's fine, these are all just expressions. And in fact, what we're going to be building anyway are these logic exp things here. So let's look at what we have. So require, that's either require of a disjunction or an external require. The external require is boring, that's okay. Disjunction, so this is the left factored xtext rewriting thing. A whole bunch of stuff with ors between them. A conjunction is a whole bunch of stuff with ands between them, and the stuff, that's either comparisons or disjunctions inside parentheses. So this is precisely the same structure you saw for the mathematical expressions on the blackboard, but for logic expressions. And I think we have the complete language now. So I think it's time we try this. Sorry. Entity plus. Here we go. So let's see. I'm a little worried that there might be something ambiguous in the grammar, but let's see. He failed. Oh no, we got warnings actually. But usually warnings are pretty bad as well. So if we have ors and ands, we are ambiguous is what it's saying. Now usually when I do screencasts at home, this is the point where I pause the video and think for a while. So this is saying that actually I just want to try something because I had the feeling that I think this might be it. So now, sorry. You know, sometimes when I this example developed a little bit differently from the last time I programmed it. No, that wasn't it. Sorry, I was afraid that the external here might so here's the thing, of course, that one can do.